kind of last minute. So this is a crapshoot as far as presentations go. So just bear with me. Had no idea what we were supposed to do, so I emailed Dr. Abdou, and he mentioned going over a couple of things, and I'll try to touch on those. So when is the cue going to happen? Oh, that's the cue. Great. Awesome. Okay. So I'm Brandy Walborn. I graduated from K-State in December of '09. I'm now a reactor engineer at Cooper Nuclear Station in Brownsville, Nebraska. Huh? Oh, I'm sorry, Brownville. I'm not from there, so I pronounced things wrong. Anyway, we're going to talk about reactor physics, the things you guys are learning about, and how they actually are applied in the real world. Just a quick overview of what we're going to do. Intro, talk about nuclear engineering careers, because my boss thought this was very important to discuss. We're going to talk about what fuels engineers do, what reactor engineers like myself do at power plants, and then summary and Q&A. So a little bit about Cooper. It is a General Electric BWR Type 4 boiling water reactor with a Mark I containment. It produces 810 megawatts electric on average, about 2,419 megawatts thermal. It has a core diameter of about 18 feet. There are 548 active fuel assemblies with 137 control rods. It is the largest single electric generating unit in the entire state of Nebraska. It doesn't mean it produces the most power, it just means out of the only single unit, it's the one that produces the most, because there's a coal station that makes a little bit more. So what are some of the jobs available for nuclear engineers? We're going to start with the non-utility options. Fuel vendors, and these are the people that actually build and design the fuel for the cores. They also do other components like radiation detectors for measuring core power and things like that. Another big one is computer codes. We have several programs, one of which I'm going to discuss here, that actually monitor the core and stations and things going on in the plant. National labs. Great government research options are out there. There are a bunch of test reactors in the southwest mainly, and some over in the east coast. And they do a lot of military support and just nuclear research in general. Universities have a lot of options for research. Obviously, I'm assuming you guys have the lab to go with this and are really familiar with the reactor over in Ward.
Not yet.
Not yet? Oh.
That's next semester.
I'm sorry. It'll be fun. Yes, so there's a lot of research going on there. The Nuclear Regulatory Commission also hires a bunch of people. That's mainly for oversight, regulation. There are two guys on our campus, or on our property, that hang out from the Nuclear Regulatory Commission. And then there are a bunch of specialized companies that deal with like waste removal and things like that. In the utility sector, reactor engineers, which is what I do, are really prevalent. Pretty much everything you do is motivated by protecting the core and making the public safe. We use a lot of computer codes that have been developed by companies like Studsvik and a couple other places that pretty much just monitor core conditions, and we can run predictions and predict what's going to happen in the core later on in life and keep up on how the detectors are running, things like that. Any kind of plant maneuvers like rod movements, anything like that, that all has to be done through us. So plant startup and shutdown, we're behind all of that. You can't just go and press buttons and start the plant up. It's a very long process with a lot of paperwork. We also handle a bunch of other issues that are related to the fuel or the reactor core. When we get new fuel, we're the people that have to inspect it and make sure it's all up to par before we can put it in. Reactivity management is pretty much just anything, like any work that's going on in the plant. If that can in any way affect the core, it's our job to make sure that it doesn't do it negatively. And if it does, we have to report it and come up with other options of things we can do. So for fuels engineers at the utility, these guys, everything fuel related, like the name says. They use computer codes to pretty much model the core currently in its current condition, and then also design options for future core setups. They use different codes for like fuel lattice, which pretty much just models different portions of fuel bundles or assemblies. Nodal codes will actually do the entire reactor core, and then transient codes measure things that are like time dependent and kind of accident analysis related. They're also the main interface for fuel vendors who design and build the bundle for the core. So let's go into what fuel engineers do in a little more depth. They pretty much design the core and well, they design the core and the fuel. The fuel at Cooper anyway is 14 feet long. It's in a 6 by 6 inch array, It contains 92 rods or pins. They're used interchangeably. 8 of these pins are actually used to hold, hang on, let me try this. There we go. The bottom plate and the top plate together. So when you pick the bundle up, that's actually doing most of the support. There are also 2 right here. If you can see them, I don't know. Little larger openings in there. They're called water rods, and that pretty much just allows water to come up for cooling and help with heat transfer in the bundle. Every single bundle has to be custom designs. So down to the pellet in each rod, the enrichment and the burnable poisons are all pre-calculated and predetermined, and then we send that information to the vendor, and then they build us the fuel. So our fuel is between 1.6 and 4.9% enriched. It's a high-density ceramic uranium dioxide pellet. And the reason those vary, any idea why we would vary the enrichment throughout the bundles?
Flux.
Exactly. Flux and core location. Because some parts of the core are not going to have as much exposure and are not going to have as high of a flux, so you want to balance that out. This is a drawing of our control blades, well, some of them. We have 137 control blades. Not all of them are like this, but they're all in the cruciform shape. So a fuel bundle is going to go here, 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 and here, and that forms what's called a fuel cell. And then when you move the rod, it goes up and down in between all of those 4. So fuels engineers also do deal with fuel management again. So why would we use burnable poisons? Anyone? Come on, go ahead.
We're going to build in excess reactivity.
Exactly. We only have a refuel outage about every 18 months. I'll talk a little bit about that later. So that's when we put new fuel in. So until then, we have to make sure that we can continue operating through that time. And burnable poisons, we use gadolinium. We add it to certain fuel pellets in the bundles. That helps us achieve this. What happens usually is that in the beginning, the core, as it first starts out, right here, you'll see it's not super energetic. There's not a lot of excess reactivity, but as time goes on, when the burnable poisons start to burn out, you then have all of the uranium that was being not used up by the burnable poisons, and then it starts to deplete rapidly near the end of the life cycle. So when you design a core, what you do basically is you shuffle older fuel elements out, or older fuel elements around the core. You take the oldest ones or the most depleted ones out, and then you put new ones in. So all of these little red ones are the fresh fuel that we have put in, I believe it was a couple years ago in a different cycle. As I mentioned earlier, there are 548 fuel locations. The bundles end up staying in the cycle for 4 to 5 reloads. A reload, as I mentioned earlier, is every 18 months, so we take out about 1/4 to 1/3 of the core and just replace it with fresh fuel. Cooper right now is in the process of transitioning to 24-month cycles, so instead of the 18-month, every 2 years we would then go into an outage. And at that point we'll probably start changing out about 188 bundles. So let's talk about what reactor engineers do. Core management. Pretty much anything that has to do with online operations, so while we're up and running, all of that stuff. Startup and shutdown, as I mentioned earlier. Rod pattern exchanges, those are done about every 90 days. So what we'll do is, right here, this is like the current rod pattern, and what we're going to want to do is we're going to want to pull these rods out and then end up with this pattern by pushing these rods further into the core. In a BWR, the rods come in from the bottom, so that's kind of a little confusing if you're not used to that. But we do this because these rods here are having more exposure than these are, and we want to balance that out and be able to everything's for the longevity of being able to run and operate for the 18 months. Sometimes you have to, after a certain amount of power is really not controlled by the control rods anymore. It's controlled by the coolant flow through the core, and that can be variable from day to day, or it can be constant for several months. Again, when you're dealing with core things, you have a bunch of restrictions. Thermal limits, so the total power across a bundle or the power across an individual pin and just power distributions in general are all taken into account, and that can be kind of tricky. We'll talk a little bit about that. You also have operational constraints, which you have to stay within the designs of your safety analysis. And this right here is what we call power and flow map, and anything that is inside the white region is where we're allowed to operate. Anything is gray is we have no idea what happens there, so we don't operate there, and then these are bad. But pretty much what happens is this is pump capacity this way, and then this is core flow this way. So you want to maintain something that's nice in here. And we use this also when we're dealing with rod exchanges to make sure that we don't burn out or run out the pumps or put us in exceeding thermal limits. Core management software. As a reactor engineer, at least at Cooper Nuclear Station, we use Gardel, which is one of 2 softwares that I know of in the industry. And this just monitors the core conditions at all times. It monitors thermal limits, your heat balance, and feed water flow, and these are just examples. It measures everything. And then we can also use it to run predictive codes, like I mentioned earlier, to analyze future core conditions and transients and accident analysis, things like that. So this is the user interface for Gardel. As you can see, we can have the power and flow map, and then you have various conditions that you're looking at for like power distribution, and then these right here are for our power detectors that are measuring the power that's actually in the core. You can map all sorts of things. It's got a lot of options. It's kind of fun. This is just another screenshot of things we can do. This actually depicts the power distribution across a pin, or I'm sorry, not a pin, a bundle in the core. So we know how hot it is, and then how much margin you have before you breach cladding. That's a big no-no. I'm not sure how familiar you guys are with how fuel works, but you have fuel meat and then you have fuel cladding, and you do not want to rupture that cladding. So Gardel helps us make sure that that doesn't happen. And this is just an example of predictors that we run. So pretty much you just put in, you know what the current core thermal power is, the flow for the feed water pumps, and then you can have it find out what your pressure is, what your K effective eigenvalue value is going to be, and it'll just output all of this. It's really quite awesome. Have you guys used MCNP yet? Okay, so that takes like what, 5 years to run? Yeah, this is done in like 30 minutes is the longest I've ever taken to run a code, and that was because I was running it for an advancement of 3.5 weeks, so it has to do all of the predictions for that. So it's really fast, and most of the things in power industry are based more for the speed than intense accuracy like they are for MCNP. So some more reactor engineering duties. During a startup, we have to do what's called an estimated critical position, and you pretty much just calculate when the reactor goes critical, which really seems lame, but it's kind of exciting the first time. And you also have to calculate your shutdown margin, which, Jeff, means what?
It's the amount of excess or negative reactivity.
Yeah, to put the core in safe shutdown condition. We're also doing a dry cask storage campaign, because back in the day, the government promised us in the power industry that it would provide a facility for power plants to dispose of nuclear waste. They have yet to come through on that promise, so a lot of facilities, since they don't have room in their spent fuel pools, have to actually store it on site. So when you do that, you pretty much have to figure out the casks that you're using, the bundles that are going in there, their age. You have to make sure they can't go critical. You may have to make sure they don't have any history of being a leaker or anything like that. And then you put them in the cask, you seal them up, and you keep them outside, and they're cooled by the air. Rod exchange packages, kind of talked about this earlier. When you want to move rods, you can't just go press buttons and move it. It requires a lot of paperwork, and we're the people that pretty much do all the paperwork and tell the reactor operators what to do. Special nuclear materials is the inventory of plutonium and uranium products. This is really not boring, but the NRC requires you to have an inventory of everything you own. And if you don't have it, you go to jail. So it's kind of a big deal. We also are in the control of any kind of fuel movements and the inspection of fuel. This is the results of a fuel inspection. It's kind of hard to see, but right here is a breach. And what probably happened, hang on, let me explain this better. Okay, so you see these lines? The dark lines are the spaces in between. The brown ones are the actual fuel bundles. They're inside of a sheath. Okay. So what probably happened is a piece of wire or whatever got in here, and then during like operations, because of the flow through it, it started to vibrate, and eventually it breached the, whoops, nuts. It breached the cladding, and then you have this little plume here is just evidence of your gases escaping out of the fuel. So during a fueling outage, which happened every 18 months, but for Cooper in 2012 are going to start to 24-month cycles, you pretty much open up the reactor, you take out all the old fuel, you put in new fuel, and then you shuffle the older fuel. We choreograph all of this. This is done months and months in advance. And this is an example of what you kind of have to do. When you take fuel out of the core, you have just the control blade that's sitting in there unsupported, so you have to put in what are called blade guides, and these just depict blade guides. And they're just used to support the the control rod while there's no fuel surrounding it. That's pretty much it. So in summary, you have a lot of career options. Reactor and fuel engineers are pretty integral to the operation of nuclear reactor plants. And a bunch of responsibilities include fuel management, core design, and core monitoring. Any questions? Yes, Jeff?
How many engineers are involved with the actual operations of the plant instead of the engineering behind the scenes?
Okay, so operations, you don't have to have a degree to be an engineering degree to be in. But there are a bunch of people in ops with degrees. And I have no idea how many are in ops. I know that we got kicked out of our office because there were too many of them in their old office. So, yeah.
So basically, they're better than you? Take your office?
No, I guess.
Or was your office just prime location?
It's actually kind of a crap location. It was not that great of a location. It was just a little bit bigger. It had one window. So, I mean, if that's really what they were vying for, because I don't think we had one window, yes.
That's intense.
It was. My cube was nowhere near it.
So what's like an advancement from
The reactor
where you are
engineer?
now?
Reactor engineer supervisor. You can, yeah. You can either stay within reactor engineering or you can go into fuels engineering, or at Cooper you pretty much have the opportunity to move around throughout various systems. Yeah, anywhere.
And that's not just specific to Cooper. It's basically an industry thing. If you start working at a nuclear facility, you're going to have the opportunity to do essentially anything you want. If you have the drive and you show that you can do it, it's pretty easy to bounce around from one thing to another.
Yeah.
Did you get your master's?
I do not. I could get it, and Cooper has a really great program where they'll do tuition reimbursement. So you can get it while you're working there, and they'll pay for it, essentially.
Have you used your education from the new courses here a lot in your job, or is it more on-the-job training?
More on-the-job training. As an engineer, yeah, you have to have the background knowledge. But, like, transport and diffusion codes? Nope. Not at all. Sorry. That's what programs are for. Yeah.
Do you guys do a lot of programming, or is that more in the fuel engineers?
Not really. That's more on the vendor side. We purchase the programs. But, I mean, fuel, not really. Just, yeah, running the codes. Go ahead.
Being as you were an SRO here,
Mm-hmm.
do you think that kind of, gave them a, hey, let's look at her first, or?
Definitely. Yeah. My reactor experience at the research reactor here totally helped out in getting this job. Or most jobs like that I got interviews for, yeah. And then turned down. Go ahead.
With your 24-month cycle, do you know how you're achieving this 6-month boost? Is it via geometry effects? Or?
Nope. We're going to just increase. We're
the
not
enrichment of the fuel.
Yeah, the
in this
enrichment.
last reload that we did, the fuel was a little richer. As a result, our most recent refueling outage actually ran long by 27 days.
Wow.
There was
long, complicated.
a transformer, yeah.
Transformer blew when we
On
were
the
running
diesel
tests.
generator, and that company doesn't exist anymore. And
Had to have another
reverse engineer.
transformer. Yeah. So it turned out to be a huge pain in the neck. But because of that, the way the fuel works out, with it being enriched so much more than what we had been using in the past, we actually had to push back our next refueling outage 2 weeks just so we can get the most efficient use out of our fuel. So that's how that worked out.
Yeah. But we're not adding any more fuel. We're not adding.
Right.
There was kind of discussion about replacing our dummy bundles, which that's a fun fact. There were 2 plants in the world that had dummy bundles, which when Cooper was designed, they didn't want it to go to full capacity, so we have 12 dummy bundles, which look and feel exactly like regular fuel bundles, except they don't have fuel in them. Now there's only 1 plant in the world, because Fukushima doesn't exist. And Drew will tell you all about that.
Fukushima exists.
It does.
It's just,
No, right?
it's a huge and tremendous snafu.
God, she's still there.
It's still there, yeah. bumpers don't really matter anymore. It's weird.
Fukushima will never be
Suppose
done.
you get some something like that.
I don't know. We're trying to get like their fuel support pieces or something. I don't know, which are kind of hard to come by because they were looking into buying them, but now they don't need them anymore. So we think we can get it for real cheap.
You know.
Yeah. It's gonna be a little while before we're running again. So.
If ever.
Yeah.
I'm Drew Niehaus. I'm in charge of the PR for Cooper Nuclear Station. Basically going to just run through with the nuclear operations in a post-Fukushima world, which is going to be interesting. Obviously, as you guys know, when it comes to nuclear is unique. We're going to touch on that a little bit, why it's so much more interesting and complicated than coal plants, which I'm sure you're all well aware of. A little bit on the Fukushima accident, some of the differences between the U.S. and Japan, the recent flooding that we've had in the Midwest, especially for us and more so OPPD's plant, Fort Calhoun Nuclear Station, and some of the political and regulatory responses. Okay, nuclear is different. You guys know that. It's not something you can just walk in and say, hey, what are you guys doing when you open up the control room? You don't get to do that. We obviously take nuclear safety very, very seriously. When you get to any nuclear power plant, they're going to tell you one thing. We have one mission, and it's not generating power. Our mission is the health and safety of the public. Generating energy is a side effect of that. You're not going to insult your intelligence. I mean, you can read all those. One of the big things that we have versus other plants, though, is the security down at the bottom. As a result of 9/11, our security department is actually the most people out of any department at the facility. At Cooper, we have roughly 730 people at the plant, and about 150 of that is armed security forces. All right, so Fukushima, what do you guys know about it? Anybody? That's true. Do you know what happened?
The generators were flooded and unable to remove heat from the reactor.
You're about 3/4 of the way there. The generators weren't flooded. The generators were actually washed out to sea. Yeah, they don't exist anymore. They're in the Pacific Ocean, which is kind of astounding when you think about the diesel backup generators are the size of a locomotive. And there was that much force behind that water to just wash them away. Now, what happened that day, March 11th, is, which one's the laser?
Top one, yeah.
1, 2, and 3 were all operating normal. 4, 5, and 6 over here were all in cold shutdown for refueling outages and maintenance. Now, what happened was you can see their water walls. The water walls were actually constructed about 25 feet. They were designed. They knew in this location they had the potential to get hit with a tsunami. I mean, it's Japan. They have earthquakes all the time. When the earthquake hit, their safety systems all started right up. I mean, this was the biggest earthquake that Japan had ever had. I mean, it was roughly a 9.0 on the Richter scale. That's a huge earthquake. Everything was going fine. About 55 minutes later, they got a 40-foot wall of water traveling between 400 and 500 miles per hour. That 40-foot wall of water was about 27 feet higher than what their water walls were built to. That's what happened. So, their diesel generators washed out to sea, fuel tanks washed out to sea. We've come to find out recently that their battery backup system, their DCs, which are supposed to last for 4 hours, wouldn't have worked. There was so much water that went everywhere, it flooded their systems. I'm going to back up a slide here. Now you can see their intake structures along here. We've also come to find out that it didn't matter that they didn't have battery backup. It didn't matter that they didn't have diesel generators. Their pumps got flooded and were fried. There was no way they were going to be able to pump water into the reactor. This was inevitable at this point. So, can't get cooling water in. That's what happens. They had a hydrogen buildup. Boom. That was unit 1. So when this happened, they're not getting water in. They've got their residual heat. Their fuel pools are starting to evaporate. Really didn't take long. With fuel pool evaporation, eventually your spent fuel bundles are going to melt. I mean, they've got enough energy to do it. Now, as a result, direct result of all this, we have a plan of the day every day that comes out and says, you know, what we're running at, what the river elevation is. I mean, it's just this huge list of information about things that are going on around the plant, as well as emergent work, just status of everything. One thing that had to be added to that was the time for the fuel pool to hit 200 degrees. And you're probably asking, okay, why 200 and not 212? Water boils at 212. Well, come to find out, the water in their fuel pools never actually hit 212 degrees, but it still evaporated off. The reason for that was, in localized areas, it did hit over 212 degrees, but as a whole, it never hit that. So we know now that if the fuel pool is at 200 degrees, we're losing water. We're losing water pretty regularly. So this is what happened afterwards. Unit 1 had the first hydrogen explosion with the buildup. Unit 3 had pipes that were linked to Unit 4. So Unit 3 blew from a hydrogen explosion. Well, Unit 4, it was in cold shutdown and should have been running fine. Unfortunately, because they had no off-site power, they had no diesel generators, they couldn't operate a valve. So hydrogen from Unit 3 leaked into Unit 4 and caused the explosion there, even though it was in cold shutdown and everything was opened up. This is after the explosion. Now, one of the things that initially we thought was different between our design and the Japanese designs was hard pipe venting, that we could vent our reactor vessel and get some of that hydrogen off and go through our ERP towers, our elevated release points, which are similar to these here. We've come to find out here within the last month or two that no, the Japanese actually had that same venting, which was a safety system installed in the 80s, I believe, is when it was installed. I'll have to check on that for sure. But the difference is our operators have the freedom to go ahead and flip a switch and get the hydrogen out. The Japanese did not have that freedom. Their culture is so different from ours that it's basically submissive. So when they run into problems and they need to vent this hydrogen, they actually had to get permission from the Prime Minister to do so. That's why these blew, because they didn't have permission to vent the hydrogen. They knew this was building up and they knew this was going to happen, but they didn't get permission. Here they are a few days later trying to restore off-site power. Why is off-site power important? Bingo. Didn't really matter. They didn't have pumps. If you look, this here is basically a concrete pump. It's what they use for laying concrete in huge amounts, vast parking lots, the middle of the parking lot. They'll use something like that where it's basically a giraffe neck sticking out and pumping. And they're just shooting water in there in hopes to get enough water in there so it doesn't boil off. This is the interior of some of these buildings. Those are 7-foot steel doors that got hit with the wall of water. That's the amount of force behind it. And if you look, you can see the circuitry. They were doomed. I mean, it was just realistically an act of God. I mean, there was no way this wasn't going to happen with that amount of water coming at them. Now, this here is Unit 4, and you can see the vessel head from it being a cold shutdown after the explosion. Now, ordinarily, you wouldn't see that. So they're throwing all this water around to try and get everything cool. They've got water everywhere, and here come to find out that just thousands and thousands of gallons of radioactive water are leaking back into the ocean. So they're now installing these locks to try and prevent that from happening. They've got debris all over the place that is contaminated. What do you do with it? They've got all sorts of problems. It's getting better, it really is, but it's going to be a long time before it's back to normal. Another problem that they've run into is that there was so much contamination around there that the ground itself was contaminated. So what they're doing here is essentially spraying in epoxy to glue everything to the ground, so when the wind kicks up, it can't blow it out to sea. So they've got all this seawater that's contaminated that they've been trying to pump in and cool the reactor and cool the fuel pools. And now they're going back in at this point and filtering the water that they've been pumping in there. They're sucking it back out. I want to say it's somewhere between 95 and 100,000 tons of contaminated water that they're dealing with. And now they're trying to filter it and use their resins to clean that back up and keep reusing that water instead of just making more and more contaminated water. They had to bring in separate storage tanks for all of this, and that's what these are. Approximately 3,000 contractors flown in. They actually have a large retired segment that wants to come in and help with this, but the government's not letting them because they're saying they're too old. The reason retired people want to come in is because, well, they're old. There's been several interviews with these guys where they're saying, hey, we're old, we don't really have a future, let us deal with all of the radiation and let these young guys, live their lives. But that's not really happening at the moment. These are some of the differences, the major differences between our plant and Fukushima. As you can see, we added 2 spare diesel generators and another portable water pump. The containment vent, which is the hydrogen vent that I just discussed. Any questions on any of those? So now what? Here we are in the Midwest, 2011, dealing with flooding. Now this is as worse, or the worst it was through all of the Midwest floods. This isn't Cooper, this is Fort Calhoun, this is the OPVD plant. Now, did you guys see anything on the news about any of this? And what'd you see?
A lot of panic.
Bingo. Fort Calhoun, when all this went down, was about halfway through the refueling outage and in cold shutdown. Now for us, we had just started up when all the water started coming. We had only been operating about 3 weeks after our refueling outage. Now one of the things that happened at Fort Calhoun, if you look along here, you can see that black. That's a water dam. It was a tertiary form of water prevention into the building, I guess. It's not their main system. It was just meant for keeping the water further away. Now, the NRC decided with Chairman Yatsko that they were going to come out and inspect both Fort Calhoun and Cooper, and then gave us 3 days notice. So we've been dealing with flooding all summer long at this point, and we now have just panic because we have to get everything cleaned up and looking nice. So to Fort Calhoun. A forklift operator ran into that water dam. It's basically an inner tube filled with water. He's retired now. As you can see, we have different procedures we have to go through during flood. Cooper is actually out of all of our emergency procedures. We've exited every single one of them. Fort Calhoun is very close. They've been shut down since mid-April, and it's looking like they're finally going to start back up sometime in the middle of next month. Now, they're going to be inspected fairly heavily by the NRC prior to startup just to make sure that water hasn't damaged any of the systems, but you got to realize that the plants were both designed to withstand this. We're designed for worst case scenario plus 10 or 20%. This is the difference in the two floods. This is Cooper here. This is the 93 flood. And you can see that on the Missouri side of the river, pretty bad. Nebraska side, not so bad. There's a specific reason for that. Anybody in here from Missouri? I'm sorry. Your levee is 6 inches lower than ours. On your side of the river, as soon as the river starts getting high enough, it's going to flood Missouri every time before it floods our side. These are just some of the flooding pictures in the area. This is the town Brownville. It's 3 miles north of the plant. Interstate 29 is right about there. That breach in the levee eventually got to be about 1,000 yards long. This is about a half mile north of the plant. This is a state park. These are our levees. The water actually got high enough, and obviously our levees are dirt. That's all they are, compacted dirt. So over time, they're not going to be one constant level across the top. So there was actually points where our side of the levee was having water splash up and over. So we actually had to add sandbags to the top of our levees. Part of our safety system. As part of our flood plan, these are HESCO barriers. There's 3 foot by 3 foot by 4 foot tall sandbags that weigh over like 2,500 pounds, too high. We actually went to the point of putting sandbag barriers on the internal and external reactor building doors. Just more flooding pictures. The Chairman Yatsko visit, which was a pleasant day for everybody. Now, as a result of Fukushima, President Obama sent in some of our NRC folks over, wanted to get a better handle of what was going on. They established a task force, and here, not too long ago, just a couple weeks ago, they released their 90-day report about Fukushima. A lot of politics involved with that. The industry as a whole, quite frankly, thinks that it's too soon. We're still learning what happened at Fukushima. We don't know all the facts. There's a very good chance we're never going to know all the facts. So 90 days to start making rules that need to be in effect 5 years from now is, in a lot of people's eyes, jumping the gun. Yeah. July 12th it came out. These are some of the recommendations. As with any disaster, as with any positive aspect in nuclear power, we're going to learn from it. If somebody does something good, we want to mimic that. The nuclear industry is one of the few industries where plagiarism is encouraged. We cheat off of each other. If somebody's doing something great, we want everybody to do that. Quite frankly, it takes one accident in the United States to put an end to nuclear power. The United States public is just fickle when it comes to it. As long as they don't have to hear about it, they're fine with it. So these are some of the issues that we're dealing with, the short-term actions. Ordinarily, there's a regulatory process. It goes out, the public gets to hear about it, we get to hear about it, IMPO gets to hear about it. That's not the case with some of these rules that are getting put into place post-Fukushima. Stop, yeah. Any questions? Anything at all? Okay.
Thank you for our presenters.